Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at minimal spanning trees. We don't really have a lot of hope of being able to do this unless we actually know what minimal spanning tree means. Now, you probably are familiar with the word minimal, so let's start at the other end. What is a tree? Well, a tree is just a series of edges with no cycles. What does that mean? Well, remember, a cycle is a path from one vertex through other vertices back to where you started. This is a cycle because you go through vertices and end up back where you started. So too, this here is a cycle. So this here does not constitute a tree. However, if I take just some of the edges, I can make a tree. These edges in blue will form a tree. Okay? So all of them form a tree, just those blue edges, for example, and that's because there are no cycles. In other words, there are no cycles because you can't start at one vertex and get back to that vertex without going over the same edge more than once. So this is a tree. What makes something a spanning tree? Well, it becomes a spanning tree if it visits all vertices. So this here in blue is not a spanning tree because it doesn't include all vertices. In particular, it doesn't include F. But if I just add in this edge here, in blue, I have a spanning tree. Once again, it's a tree because the blue edges have no cycles. You can't start at one vertex and go back to that vertex without traversing the same edge. That's why there are no cycles. And that tree is a spanning tree because it includes all of the vertices in the network. So, what then do we mean by minimal spanning tree? Well, we learned in a previous lesson that sometimes we have graphs like this that are weighted. There are weights along each of these, and they could represent anything. So in this example, let's pretend that each of these nodes represents a building of an organization, and each edge is the cost of cabling. We want to set up computer networks such that every building is connected to every other building. So each of these numbers could represent the cost of cabling. So what we want to do is we want to find a spanning tree here. We want to find a tree that visits each of these buildings, each of these nodes, but the cost of cabling is as low as possible. So how are we going to go about doing that? Well, it doesn't actually matter where we start, so we're always going to start with the edge that has the lowest weight, and that one is here, that 20 there. So we're going to connect H and K like that. So then let's go from K. What is the next lowest weight from K? Well, it's 30. 30 is the next lowest after 20. So I'm going to include this edge here. All right, now let's repeat the process. What is the next lowest weight from L? Well, it's not 60, either of these ones, it's 40. So I'll include 40. But here we have a problem. See, we've ended up at M. We can't go backwards like that because that would waste money. We're already connected K to M through L. So let's go back and let's find the next lowest weight in the entire graph. Well, that happens to be this one here, this 30. We want to include this edge here because it's a low number. So then let's go from I. What is the next lowest weight from I? Well, that's the 40 here, so we're going to include that. So you can see that these edges in green clearly form a tree. We haven't yet formed, however, a spanning tree because there's one vertex, in our example, that's one building that's not included. So what are we going to do to include that? Well, we're going to need to include an edge that goes to J, and we're going to choose the edge with the lowest weight, which is obviously this one here. So here we have in green a minimal spanning tree. So the cost of cabling is 30 plus 40 plus 50 plus 20 plus 30 plus 40. It is 210 all up. That is the minimal cost of cabling. We did that by finding the minimal spanning tree. Now, I just want to point out that this number we get, 210, is unique. There's always going to be only one possibility for the minimum possible sum of the weights. However, there may be more than one spanning tree that achieves this. It doesn't matter which one you get as long as you get the lowest number as your final answer. And we did that here by starting with the edge with the lowest weight, then going from that vertex, getting the edge with the next lowest weight, and so on. When we got to a point where we couldn't continue any further, we just started the process again. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.